Imagine there is a dial in front of you, and turning it makes smaller things visible. Turn it a little, and cells appear in a drop of pond water. Turn it further, and X-rays lay out the atoms inside a crystal. Further still, and 27 kilometers of superconducting magnet beneath Geneva resolve structure at 10 to the minus 19 meters. 1 billion times smaller than a single atom. The dial has never once lied to you. More energy, more detail. That is the entire history of seeing. But here is what nobody mentions while you are turning it. Somewhere past that point, the image at the center stops sharpening. It goes dark. And when you turn harder, the way you always have, the darkness does not clear. It grows. By the end of tonight, you will know exactly what fails down there, and why nothing anyone ever builds will fix it. Before we begin, if questioning things this slowly is how you like to fall asleep, a quick like or subscribe really helps this channel grow. It's a small thing for you, but it means the world to me. Now, let's begin. Nothing you have ever seen came to you directly. Every object you have ever looked at, every face you recognize, every word on every page you have read, arrived in your eyes as light that bounced off something else first. Seeing is not a thing you do to the world. It is a thing the world does to you, after you have thrown something at it and waited for the return. That sounds like a poetic way of putting it, but it is meant literally, and it is the foundation of everything we are going to do tonight. To see anything at all, you need exactly 3 ingredients, and in the whole history of human observation, nobody has ever found a 4th. You need a source, something that emits. You need the object, the thing you want to know about. And you need a detector, which for most of history was an eye, and is now more often a sensor, a photographic plate, a crystal, a wire chamber. Light leaves the source, strikes the object, and some fraction of it scatters into the detector. What comes back carries information about what it hit. Everything follows from that arrangement, including, as we will find, a wall. The critical part of the arrangement is the middle step, the scattering, because scattering is fussy about size. A wave will only tell you about a feature if the wave is roughly the same size as that feature, or smaller. If the wave is much bigger than the thing might as well not be there. The clearest way to feel this is to think about a boat on the sea. Picture a small fishing boat, 10 meters or so from bow to stern, sitting out on open water. Now send it a swell, one of those long, slow ocean waves whose crests are 1/2 kilometer apart. What happens to the boat? It rises, then it falls. The whole hull goes up together and comes down together, because the entire boat sits inside a single gentle slope of that wave. The boat rides. And here is the important half. The wave rides too. It carries on toward the shore, essentially unchanged, unmarked, carrying no information whatsoever about the fact that a boat was in its way. If you stood on the beach and studied that swell as it came in, you could not tell whether it had passed a fishing boat, a buoy, or nothing at all. Now change the water. Instead of a long swell, send a short, sharp chop, waves a couple of meters from crest to crest, comparable to the boat itself. Suddenly the picture is completely different. The waves break against the hull. They reflect. They scatter around the bow and interfere behind the stern and set up a complicated pattern that spreads out across the surface. And that pattern is not noise. That pattern is a description. If you were clever enough at reading water, you could reconstruct the shape of the hull from the way those waves came off it. That is the entire rule, and it is worth saying it in the plainest words available. Long waves do not feel small things. If you want to know about something, you have to probe it with something at least as fine as the thing itself. Nothing about this is a limitation of our equipment. It is not a statement about lens quality or sensor noise or how steady your hands are. It is a statement about information. A wave that is much longer than an object simply does not carry away a record of that object, and no amount of ingenuity at the receiving end can recover a record that was never encoded in the first place. You cannot sharpen a photograph of something the light never noticed. So we have our rule. To resolve a feature of a given size, use a wave of comparable size or smaller. And immediately, sitting inside that rule, there is a promise. Because if the only thing standing between you and a smaller world is the length of your wave, then all you have to do is find a shorter wave. And there is always a shorter wave. That is the seductive part. Nothing in the equations that describe light sets a floor on wavelength. You can halve it, and halve it again, and go on halving forever, as far as the mathematics is concerned. Every step down that ladder should reveal a finer layer of the world. There is no obvious point at which the universe would put out a hand and say, this far and no further. Which means that if you had asked a physicist in, say, the year 1900, whether there is a limit to how small a thing we can see, the honest answer would have been no. Difficult, yes. Expensive, certainly, but not impossible. Just keep making the light finer. That instinct is very old, and it is worth naming because we are going to come back to it more than once tonight. It is the instinct that says, when you cannot make something out, bring a brighter lamp. It is what you do in a dim room when you are trying to read the small print on the back of a packet. It is what medicine did, and what metallurgy did, and what biology did. When the picture is not sharp enough, throw more light at it, turn the lamp up. A brighter lamp, hold on to that phrase. It is going to change meaning 3 times before we are finished, and by the last time it will not be comforting at all. Because there is a cost hidden in that ladder, and nobody quoted it to you at the start. Going to shorter waves is not free. It is not even close to free, and the price does not stay small, and it does not level off, and, this is the part that takes an hour to earn, the price eventually turns around and buys you the opposite of what you paid for. That is the story tonight. We are going to walk down the ladder of seeing, rung by rung, from the first crude microscopes through to the largest machine our species has ever built, and at each rung, we are going to ask the same question and get an answer that keeps working. And then we are going to take one more step, the step that should be no different from all the others, and watch the entire logic of observation fold in on itself. The place where it folds has a name and a number. The name is the Planck length. The number is about 1.6 times 10 to the minus 35 meters, which is a quantity so small that every comparison I can offer you will fail, and we will spend a good part of tonight failing at those comparisons together. What matters more than the number is what happens there. Below that scale, the act of looking closer does not fail because our instruments are crude. It fails because the universe, using nothing but the laws we already know and trust, arranges for the thing you are trying to look at to disappear. And the strangest part, the part that keeps this from being a merely technical curiosity, is that there are 2 completely different ways to prove it. 2 arguments that share almost no ideas, no equipment, no era, and no assumptions except one. 2 roads, and the same wall at the end of both. So here is the question I want to leave sitting in the room with us, the one we are going to circle for the next 2 hours before we answer it properly. If seeing is scattering, and scattering just needs a fine enough wave, and there is no shortest wave, then what, exactly, breaks? What is it about the world, or about us, or about the relationship between the two, that puts a flaw under how finely reality can be examined? And when we finally get down there and find that flaw, what is it actually the flaw of? By the end of tonight, you will know exactly what fails, and why, and what it costs us to admit it. But we are nowhere near ready to answer that yet. First we have to earn it, and we earn it the way physics earned it, by climbing down the ladder ourselves and finding out how far it goes. Let us start at the top, with a piece of ground glass and a candle. The first people to look through a good lens had no idea what they were about to find. In the 1600s, when the earliest serious microscopes were being ground and assembled, the general assumption was that the world got simpler as it got smaller. Take a leaf, magnify it, and you would see a finer version of a leaf. Take a drop of pond water, and you would see a smaller drop of water. Instead, they found a menagerie. A single drop from a rain barrel turned out to contain hundreds of things, swimming, spinning, dividing, eating one another. The tissue of a plant turned out to be built from boxes, tiny compartments stacked like brickwork, which is where the word cell comes from. There was a whole living world sitting a few centimeters from the human eye that no human had ever seen, and it had been there the entire time, invisible for no reason other than scale. That first descent was enormously productive, and it ran into a wall almost immediately. The wall is the wavelength of visible light. What we call visible light spans roughly 400 to 700 nanometers, a nanometer being a billionth of a meter. Blue at the short end, red at the long end, everything you have ever seen in between. And by the rule from the last part, that wavelength sets the finest detail that light can bring you. The German physicist Ernst Abbe worked out the exact form of the limit in 1873, while he was designing lenses for Carl Zeiss. What he found was that no matter how perfect your glass, how flawless your grinding, how expensive your instrument, an optical microscope using visible light cannot resolve features much finer than about 200 nanometers. It is not a manufacturing problem. It is the wave doing what waves do. 2 points closer together than that produce overlapping blurs that no lens can separate, because the information about their separation is not in the light. 200 nanometers is a wonderful resolution if you want to study a cell, which is typically 10 to 100 times larger than that. It is completely useless if you want to study an atom. An atom is about 1/10 of a nanometer across, 1/10 of a nanometer, which means that visible light at 400 to 700 nanometers is somewhere between 4,000 and 7,000 times too coarse. That is not close. That is not a matter of pushing the technology a little harder. Trying to see an atom with green light is like trying to read Braille while wearing a boxing glove. The fingers are simply the wrong size for the question, and no amount of concentration fixes it. So the wall was real. And then, as always, someone found the door. The door was to use light that is not visible. X-rays sit far down the wavelength scale from the colors our eyes evolved to catch, and the useful ones for this purpose have wavelengths right around 1/10 of a nanometer, which is to say, right around the size of an atom. Send X-rays into a crystal, and the regularly spaced atoms scatter them into a pattern of spots, and from that pattern you can reconstruct where the atoms are. That is X-ray crystallography, and it is how we know the arrangement of atoms in salt, in diamond, in metals, in proteins, in the double helix. The technique is more than a century old, and it is still doing the heavy lifting in structural biology today. Notice what happened there, because the pattern is going to repeat. There was a wall. The wall was set by wavelength. Somebody found a shorter wavelength. The wall dissolved. There is one modern wrinkle worth mentioning, because it looks like a counterexample and is not. In 2014, the Nobel Prize in Chemistry went to Eric Betzig, Stefan Hell, and William Murner for what is called super-resolution fluorescence microscopy, which routinely does better than Abbe's 200 nanometer limit using ordinary visible light. Headlines at the time said the diffraction limit had been broken. It had not, quite. What those techniques do is extremely clever, but it is a different game. They tag the specimen with fluorescent molecules and then switch those molecules on and off, a scattered handful at a time, so that in any given frame you are looking at isolated points of light rather than a continuous scene. And if you already know that a blob of light is coming from a single point emitter, you can find the center of that blob to far better precision than the blob's own width. You are not imaging unknown structure at high resolution. You are locating known point sources very precisely and building a picture out of thousands of those locations. The wavelength rule is untouched. Abbe's limit still applies to what a single frame can resolve. The trick works because of extra information supplied from outside the light. The knowledge that each emitter is a point. And that kind of trick will not save us later, when the thing we are trying to resolve is unknown structure, at a scale where the probe itself is the problem. But set that aside. The historical lesson of this part is the one that makes the rest of tonight so difficult to believe, so let me state it clearly. Every single time in the history of observation that we have hit a wall of this kind, the wall has turned out to have a door, and the door has always been the same door. Go to a shorter wave. Cells to organelles. Organelles to molecules. Molecules to atoms. Each step was declared impossible by someone competent, and each step was taken anyway, and the mechanism was always identical. Which is why, when a physicist tells you there is a flaw, a real one, a final one, you should be skeptical, and you should demand to see the argument in detail. That skepticism is correct. It is the right instinct. Nearly every previous version of this claim was wrong. So we are going to keep going down. But before we take the next rung, we have to pick up the invoice, because there is a cost attached to every step we have just described, and I have not yet told you what it is. Going from visible light to X-rays did not just change the wavelength. It changed something else at the same time, something that grows as the wavelength shrinks, and that something is what eventually ends this story. Einstein worked out what it was in 1905, and he did not realize he was writing down a wall. In 1905, Albert Einstein published a short paper about a laboratory oddity called the photoelectric effect. The fact that shining light on a metal surface knocks electrons out of it, but only if the light is the right color, and no amount of extra brightness will substitute for the wrong color. Turn a dim blue lamp on the metal, and electrons come off. Turn a blindingly bright red lamp on the same metal, and nothing happens at all. That made no sense if light was simply a wave delivering energy smoothly, because a brighter wave delivers more energy, and more energy should knock more things loose. Einstein's resolution was that light does not arrive smoothly. It arrives in discrete parcels, quanta, later called photons, and the energy of each individual parcel is set not by the brightness of the beam, but by its wavelength. A bright red lamp sends enormous numbers of weak parcels. A dim blue lamp sends fewer parcels, but each one hits harder. If a single parcel does not carry enough energy to free an electron, it does not matter how many of them you send. This was the work for which he received the Nobel Prize in 1921, and it gives us the exchange rate we need. The energy carried by one quantum of light equals Planck's constant, multiplied by the speed of light, divided by the wavelength. Written as a sentence, shorter wavelength means more energy per parcel, in exact and unforgiving proportion. Halve the wavelength, and you double the energy of every quantum in the beam. Planck's constant, the number sitting at the front of that relation, is about 6.626 times 10 to the minus 34th joule seconds. It is a very small number, which is the entire reason quantum effects do not intrude on ordinary life. And as of the 20th of May, 2019, it is no longer a measured quantity at all. It is exact by definition, because the International System of Units now defines the kilogram by fixing the value of Planck's constant. We have built our standard of mass on top of it. That is how confident we are. Now put the two things together, and the shape of tonight begins to appear. The rule from the first part says, to resolve a feature, you need a wavelength about that size or smaller. Einstein's relation says, a shorter wavelength costs more energy per quantum. Therefore, resolving a smaller feature costs more energy. Not as a side effect. not as an engineering inconvenience. As the same statement, said twice. Let us put a number on it, because a number makes it real. Suppose you want to see an atom, which means resolving about 1/10 of a nanometer, 10 to the minus 10 meters. Feed that into Einstein's relation, and each photon you need carries about 1.99 times 10 to the minus 15 joules. That figure means nothing on its own, so let us convert it into the unit physicists actually use down here. 1 electron volt is the energy an electron picks up when it crosses a 1-volt gap, the kind of push a single AA battery could give it. It is a tiny amount of energy, about 1.6 times 10 to the minus 19 joules. For scale, a photon of visible light carries around 2 electron volts. A typical chemical bond, the thing holding a molecule together, is worth a few electron volts. That is the energy scale of everyday matter, of chemistry, of biology, of you. Our atom-resolving photon carries 12,400 electron volts. 12,400 electron volts, or as it is usually written, 12.4 keV. That is 6,000 times the energy of a photon of visible light, and it is why we call those things X-rays instead of light, and it is why an X-ray goes through your hand while a torch beam does not. To see something 10 times smaller, you must throw something 10 times harder. That is the deal. It has never been negotiable, and it never will be, because it is not a rule about instruments. It is a rule about waves. It is worth pausing on how steep that staircase really is, because the numbers are easy to say and hard to absorb. Going from the chemistry of your own body, a few electron volts, up to the 12,000 electron volts of an atom-resolving X-ray, buys you a factor of about 1,000 in energy. And what does that 1,000-fold increase purchase in resolution? It takes you from 200 nanometers down to 1/10 of a nanometer. 2,000 times finer. That is a good exchange rate, one of the best in the whole story, and it is the last time the trade will feel generous. There is also something quietly remarkable about the fact that the constant sitting at the front of the master equation is now exact. When Planck's constant became a defined value rather than a measured one, the relationship between a wavelength and the energy it carries stopped being an empirical finding and became part of the scaffolding of the unit system itself. The price list is not an estimate. It is fixed, by definition, in a way that almost nothing else in experimental physics is. And nothing in the equation suggests a stopping point. Beyond X-rays lie gamma rays, and beyond those there is no named category, only shorter and harder and more expensive. The mathematics runs off the edge of the vocabulary long before it runs out of numbers. You can write down a wavelength of 10 to the minus 50 meters, and the equation will politely tell you what it costs. Let me slow down here, because I want you to feel the descent, rather than just follow it. Imagine you are holding the waves themselves, and you can shorten them at will. Start long. You are holding a swell 1/2 kilometer from crest to crest, and you send it across a harbour. The fishing boat lifts and settles, and the wave goes on, telling you nothing. Shorten it. Now the waves are a few meters, and the hull scatters them into a pattern you could read, if you knew how. Shorten again and again, until the waves are so fine that you could map the grain of the wood on the boat's rail. Keep going. The waves are now light. You are holding green light, 500 nanometers, and you sweep it across a leaf and see the cells laid out like paving. Sweep it across a single atom, and nothing comes back. The atom sits inside the wave the way the fishing boat sat inside the swell, rising and falling in a field so much larger than itself that no record of it is made. Shorten further. The wave contracts through the ultraviolet, and somewhere around 1/10 of a nanometer, it finally becomes small enough to catch on the lattice, and for the first time, the atoms answer. But your hands are heavier now. Every time you shortened the wave, the quanta got harder, and the thing you are holding is no longer light in any friendly sense. It is a stream of X-rays, and it is starting to burn. That is the bargain, and it is the only bargain on offer. Let me write it in the form we will use for the rest of tonight, because we are going to need it about 20 more times. Call it the master equation. The energy you need is Planck's constant times the speed of light, divided by the distance you want to resolve. Energy in the numerator. The distance you are trying to see in the denominator. Which means that as the distance you want to resolve gets smaller, the energy required gets bigger, and it does so without any ceiling at all. Take the resolution down by a factor of 1,000, and the energy goes up by a factor of 1,000. Take it down by a factor of 1,000,000,000, and the energy goes up by a factor of 1,000,000,000,000. The equation does not flinch. It does not warn you. It just keeps handing you the bill. For a very long stretch of history, that bill was payable. Enormous, but payable. The difference between an optical microscope and an X-ray source is money and engineering. And money and engineering are the kinds of problems civilizations are good at. But look at the shape of what we have just written down. We started out asking what it takes to see more clearly, and the answer came back as an energy, and the energy grows without limit as the target shrinks. Somewhere in that sentence there is a trap, and I want to name it now even though we cannot spring it yet. Here it is. Everything in physics that carries energy has consequences. Energy is not a neutral thing you can pour into a box without the box noticing. And if the amount of energy required grows without limit, while the box you are pouring it into shrinks without limit, then sooner or later, the energy stops being a tool and starts being an event. Which raises the possibility, no more than a possibility at this stage, that the act of looking closer might, at some point, close the door. Hold that thought. It is going to be literally true before the night is out. But first, an objection, and a good one. This entire argument has been about light. Light has to obey the relationship between wavelength and energy, because light is made of photons, and that is what photons are. What if we simply stop using light? The objection at the end of the last part is the right one, and for a while, it looked like a way out. In 1924, a French aristocrat named Louis de Broglie submitted a doctoral thesis containing an idea so strange that his examiners were not certain whether to pass it. Einstein had shown that light, which everyone knew was a wave, also behaves like a stream of particles. De Broglie asked the obvious question in the other direction. If waves can be particles, can particles be waves? His proposal was that every piece of matter has a wavelength, and that the wavelength is given by exactly the same relationship that governs light, Planck's constant divided by the momentum. Not a metaphor, not an analogy, an actual wavelength, belonging to an actual electron, and by extension to protons, to atoms, to molecules, and in principle to you, though your wavelength, given your momentum, is so preposterously small that it will never matter to anyone. It is worth being concrete about how small your own wavelength is, because it explains why nobody noticed this for 300 years. Walk across a room at a comfortable pace, and your de Broglie wavelength comes out around 10 to the minus 36 meters. That is smaller than the Planck length we are going to spend the rest of tonight discussing. There is no experiment, and there will never be an experiment, that could make you diffract. The wave nature of matter is not hidden from us because it is subtle. It is hidden because momentum sits in the denominator, and anything with appreciable mass, moving at any appreciable speed, has an enormous amount of momentum by atomic standards. De Broglie's examiners, faced with this in a doctoral thesis, sensibly sent it to Einstein for an opinion. Einstein told them it was correct. It has been confirmed since with electrons, with neutrons, with whole atoms, and with molecules containing hundreds of atoms, objects large enough that you can name their chemical formula, sent through a grating one at a time, and building up an interference pattern that only makes sense if each molecule went through as a wave. For an electron it matters enormously, And it opens up a genuinely new option, because if electrons have wavelengths, electrons can be used as probes. So let us cost it out. Suppose you want an electron whose wavelength is 1/10 of a nanometer, atom-sized, the same target we just priced in X-rays. Rearranging de Broglie's relation gives the momentum you need, about 6.63 times 10 to the minus 24 kilogram meters per second. Convert that into a speed, and you get roughly 7.3 million meters per second, which sounds enormous, until you compare it with the speed of light and find it is only about 2.4%. Fast, but not fast enough for relativity to seriously distort the arithmetic. Now the energy. Using the relativistic expression, the total energy is the square root of the momentum term plus the rest mass term, and the kinetic energy is that total minus the rest mass energy the electron has just by existing. The answer comes out at about 2.4 times 10 to the minus 17 joules. Convert to electron volts, and that is 150. 150 electron volts. To see an atom. Sit with that for a second, because it is genuinely lovely. That is not a particle accelerator. That is 150 volts, which is roughly what runs through a main socket. To resolve individual atoms with electrons, you heat a filament until electrons boil off the surface. You accelerate them across a 150-volt gap. You send them through a small hole, and out the other side comes a beam whose de Broglie wavelength is about 1/10 of a nanometer. That is it. That is the whole recipe. And it is not a thought experiment. In 1927, at Bell Telephone Laboratories in New Jersey, Clinton Davison and Lester Germer fired a beam of low-energy electrons at a crystal of nickel. What they got back was not the smooth spray you would expect from tiny bullets bouncing off a hard surface. They got peaks and troughs, a diffraction pattern, with maxima at particular angles, positioned exactly where Bragg's formula for wave scattering off a crystal lattice said they should be if the electrons had de Broglie's wavelength. They had photographed matter behaving as a wave. Davison shared the Nobel Prize for it in 1937 with George Paget Thompson, who had shown the same thing independently by firing electrons through thin metal foils. There is a pleasing detail in that. George Thompson's father, J.J. Thompson, had won a Nobel Prize for demonstrating that the electron is a particle. The son won one for demonstrating that it is a wave. Both were right. Now compare the two probes head to head, because the comparison is the whole point of this part. To resolve 1/10 of a nanometer with light, you need a photon carrying 12,400 electron volts. To resolve the same 1/10 of a nanometer with an electron, you need about 150. The electron is nearly 100 times cheaper for identical resolving power. Why? Because the electron is not starting from nothing. It already has rest mass, and mass carries momentum cheaply at low speeds. A photon has no rest mass at all, so every scrap of its momentum has to be bought with energy at the full exchange rate. The electron gets a discount for showing up with luggage. That discount is why electron microscopy became the workhorse of the atomic world, rather than a curiosity. It is why we have images of individual atoms sitting in rows on a surface. Matter turned out to be a better lamp than light. So there it is, a second ladder, running parallel to the first, and considerably cheaper. If light gets too expensive, switch to electrons. If electrons get expensive, try protons, or ions, or whatever else has mass and momentum. The universe appears to have given us options. I want to be honest with you about what happens next, because this is the last comfortable moment in the video. The discount does not survive. It is real, it is large, and it is temporary, and the reason it expires is buried inside that relativistic energy expression we used a moment ago, the one with the square root, the momentum term, and the rest mass term. As long as the electron is ambling along at a couple of % of light speed, The rest mass term dominates, and the electron is cheap. But we are not going to stay at 2% of light speed. We are going to go much, much faster, because the targets are about to get much, much smaller. And when we do, something happens inside that square root that closes this door for good. Before we let that door close, let us use it, because the next few rungs of the ladder are the most spectacular in the history of physics, and they were all bought with the master equation. The atom is not the bottom. Almost all of an atom is empty. The mass is concentrated in a nucleus about 100,000 times smaller than the atom around it, roughly 10 to the minus 15 meters, a unit small enough to have earned its own name, the femtometer. That is also, near enough, the size of a single proton. So, what does it cost to see a nucleus? Put 10 to the minus 15 meters into the master equation. The answer is about 2 times 10 to the minus 10 joules per probe, which converts to 1.25 billion electron volts. 1.25 giga-electron volts, in the standard shorthand, 1.25 GeV. Compare that with the 2 electron volts of a photon of visible light. To go from seeing a leaf to seeing a nucleus, the price per probe has gone up by a factor of about 1 billion, and in the 1960s, that price became payable. At Stanford, in California, a linear accelerator 2 miles long, 3.2 kilometers of straight, evacuated pipe, was built to push electrons to energies of up to about 20 billion electron volts, 20 GeV, more than an order of magnitude past what the master equation demanded for nuclear dimensions. Beginning in 1967, experimenters from Stanford and the Massachusetts Institute of Technology aimed that beam at targets of liquid hydrogen and liquid deuterium, the simplest nuclei there are, a single proton and a proton bound to a neutron, and watched what came back. Let me put you in the room, because this is one of the moments where physics changed shape. You are in End Station A, a hangar-sized concrete hall at the end of 2 miles of buried accelerator. The beam arrives in pulses, invisible, silent, 20 billion electron volts a particle, and dumps into a target of liquid hydrogen kept just above absolute zero. Off to one side, a spectrometer arm the size of a house swings on rails to a wide angle, far off the beamline, out where almost nothing should be arriving. If the proton is what everyone half assumes it is, a soft smear of charge, a little pudding of matter, then electrons should glance off it and continue forward. Deflecting one hard, through a large angle, should be about as likely as firing a bullet into fog and having it come back at you. The rate at that angle should be almost nothing. You watch the counters. They are not almost nothing. They are clicking steadily, patiently, far above anything a soft proton could produce. And every one of those counts is an electron that went in at 20 GeV, hit something small and hard inside a proton, and bounced. That pattern has a precedent, and everyone in the field knew it immediately. In 1911, Ernest Rutherford's team had fired alpha particles at gold foil and found a few of them coming straight back, which Rutherford famously compared to firing a 15-inch shell at tissue paper and having it rebound. Soft, spread-out charge produces gentle, forward-leaning scattering. Hard, point-like objects throw probes backwards. Rutherford's rebounds meant the atom has a nucleus. The Stanford rebounds meant the proton has contents. Those contents are quarks. The experiments, the technique is called deep inelastic scattering because the electrons lose a great deal of energy and reach far into the target, showed that the proton behaves, at high enough energy, like a loose bag holding a small number of point-like constituents. The same data also gave the first indirect evidence for gluons, the particles that bind those constituents together, because when the experimenters added up the momentum carried by the charged constituents, they found about half of it missing, carried by something electrically neutral. Jerome Friedman, Henry Kendall, and Richard Taylor received the Nobel Prize in Physics in 1990 for that work. And notice what actually made it possible. Not a new principle, not a conceptual breakthrough. 20 billion electron volts, delivered by 2 miles of machine, purchased at exactly the exchange rate the master equation quotes. It is worth dwelling for a moment on how strange the object they had just discovered is, because it shows how little the ladder had prepared anyone for what was down there. The proton is not a small hard ball containing 3 smaller hard balls. Its measured charge radius is about 0.84 femtometers, a number, incidentally, that touched off a decade-long crisis of its own, when measurements, using muons instead of electrons, came back disagreeing with the established value, by far more than either experiment's error bars allowed. And most of the proton's mass is not in its quarks at all. Add up the rest masses of the 3 quarks, conventionally said to constitute a proton, and you account for something like 1% of the total. The other 99% is the energy of the fields binding them, sloshing inside a volume a femtometer across. When you weigh yourself in the morning, almost all of what the scale reports is not matter in any everyday sense. It is confined energy. None of that could have been guessed from outside. It had to be seen, and seeing it cost 1 billion electron volts a probe. Now keep going, because the ladder does. Suppose you want to resolve 10 to the minus 18 meters, 1,000 times smaller than a proton, 100 million times smaller than an atom. The master equation is unbothered. It asks for about 1 trillion electron volts. 1 tera electron volt. 1 TeV. And we built that machine too. The Large Hadron Collider sits in a circular tunnel, 27 kilometers around, about 100 meters beneath the border of France and Switzerland, outside Geneva. It is a ring of superconducting magnets, cooled to 1.9 Kelvin, colder than the cosmic microwave background, colder than deep space, because that is the only way to carry the current needed to bend the beams around the circle. In its current running period, it accelerates protons to 6.8 tera electron volts each, and collides them head-on for a total of 13.6 TeV, against a design figure of 7 TeV per beam and 14 TeV in collision. Every part of that machine exists for one purpose, and it is the purpose we have been tracking all night. It is a microscope, a 27-kilometer, €9 billion superconducting microscope, and what it buys, with 13.6 trillion electron volts, is the ability to resolve structure at a scale of roughly 10 to the minus 19 or 10 to the minus 20 meters. At those energies, the collisions do something no gentler probe can do. They deposit enough energy in a small enough region to disturb the Higgs field itself, the field that permeates all of space and gives the fundamental particles their masses. And a disturbed field ripples. Those ripples are Higgs bosons. They exist for a fraction of a second, and then decay into other things. And it was by reconstructing those decay products that the Atlas and CMS collaborations announced, on the 4th of July, 2012, the observation of a new particle at a mass of about 125 giga-electron volts. François Englert and Peter Higgs received the Nobel Prize the following year. Let me note one detail about the LHC that captures how expensive this ladder has become. Each of the 2 proton beams, at full intensity, carries something like the kinetic energy of a high-speed train, hundreds of megajoules, enough to melt through half a ton of copper if it went astray. All of that spent on decimal places of resolution. That is what 3 more orders of magnitude cost. There is also a reason the machine is a collider rather than a longer version of the Stanford LINAC, and it is a reason worth understanding because it will come back when we start imagining impossible machines later. When you fire a fast particle at a stationary target, most of the energy you paid for goes into simply carrying the wreckage forward. The center of mass of the collision is already moving at close to light speed, and only a modest fraction of the beam energy is available to do the actual work of probing. Collide two beams head-on instead, and the center of mass sits still, and every joule you bought is spent where you wanted it spent. It is the difference between hitting a parked car and two cars meeting. That is why fixed target machines gave way to colliders as soon as the engineering allowed, and it is why the effective resolving power of the LHC is what it is, despite the fact that individual cosmic ray particles have been observed with lab frame energies tens of millions of times higher. So where does that leave the ledger? We have gone from cells to atoms to nuclei to the inside of the proton. Every step obeyed the same rule, every step cost more energy, and every step worked. The bargain has never once failed us. Which raises an entirely reasonable question. If the master equation has been honored at every scale, from a fishing boat to a Higgs boson, why should anyone believe it ever stops? To answer that, we have to go back to something I promised at the end of the last part, the thing that happens inside the square root when an electron gets very fast, because that is the moment the two ladders we have been climbing quietly merge into one. Go back to that relativistic energy expression, the one we use to price the atom-seeing electron. In words, the total energy of a particle is the square root of two terms added together. The first term is its momentum multiplied by the speed of light, squared. The second term is its rest mass, multiplied by the speed of light squared, and then squared again. The kinetic energy, the energy of motion, the part you have to pay for, is that total, minus the rest mass energy the particle carries just by existing. Two terms under a square root. One about motion, one about mass. And the whole question of whether matter is a cheap probe or an expensive one comes down to which of those two terms is bigger. At 2.4% of the speed of light, our atom-seeing electron is firmly in the regime where the rest mass term dominates. The electron's rest mass energy is about 500,000 electron volts, and we only needed 150 electron volts of motion on top of it. The mass is doing the heavy lifting. The motion is a rounding error. That is exactly why the electron was 100 times cheaper than a photon. Now push the momentum up, not by a little, by a factor of 1,000, then 1,000,000, then 1,000,000,000, which is precisely what every machine in the last part did. As momentum climbs, the first term under the square root, the momentum term, grows without bound. The second term, the rest mass term, does not grow at all. The electron's mass is what it is. It does not increase because you are in a hurry. So at some point, the momentum term becomes enormously larger than the mass term. And once one number under a square root is 1,000 times the other, the smaller one stops mattering. You can drop it. Nothing meaningful changes. And when you drop it, the expression collapses to something almost embarrassingly simple. The kinetic energy of the particle becomes just its momentum multiplied by the speed of light. Physicists call this the ultra-relativistic regime, and every particle in every accelerator we have discussed tonight sits well inside it. Now take that simplified energy and substitute de Broglie's relation. Momentum equals Planck's constant divided by wavelength. What comes out is energy equals Planck's constant times the speed of light divided by the wavelength. Look at that carefully. That is the photon equation. That is Einstein's 1905 relation, arrived at from a completely different direction, for a particle that has mass, that was supposed to be cheap, that was supposed to be our alternative. The discount is gone. Above a few million electron volts, an electron with a given wavelength costs exactly what a photon of that wavelength costs. Not approximately, not within a factor of 2, the same. And this generalizes, which is the part that closes the escape route for good. Nothing in that derivation was specific to electrons. Take a proton instead. It is heavier, so it stays in the mass-dominated regime longer. but push it hard enough, and the momentum term swallows the mass term just the same, and the proton's cost curve converges onto the identical line. Take a muon, an ion, a nucleus. It makes no difference. Every probe, once it is energetic enough to be useful at small scales, obeys the same relation. The rest mass, the one thing that made different particles different for our purposes, becomes irrelevant precisely when we start needing it. Some numbers make the crossover concrete. An electron's rest mass energy is about 511,000 electron volts, half an MeV. At the 150 electron volts we needed for an atom, the motion is worth about 1/3000th of the mass, and the electron is comfortably in the cheap regime. At the 20 billion electron volts Stanford was using, the motion is worth about 40,000 times the mass, and the rest mass has become a rounding error in the other direction. Somewhere in between, around a few million electron volts, the two terms pass each other. Everything above that crossing point is one regime, and every machine humans have ever built for probing small distances lives above it. There is also no exotic third option waiting in reserve. You might reasonably ask whether some probe could be devised that has no wavelength at all, and so sidesteps the whole relation. The answer is that having a wavelength is not a property some particles happen to have. It is what it means to be a quantum object, which is what it means to exist. Anything you can send toward a target and detect afterwards has a de Broglie wavelength, and therefore a momentum, and therefore an energy, and therefore a place on the master equation's price list. There is no backdoor, because there is no other kind of thing. So from this point in the story onward, there is only one equation, and we do not have to keep asking what we are probing with. The energy required is Planck's constant times the speed of light, divided by the distance you want to resolve. The master equation, universal. I want to pause on what that universality actually means, because it changes the character of everything that follows. Up to now, everything we have discussed has been a limitation of a technique. Optical microscopes hit a wall, so use X-rays. X-rays are expensive, so use electrons. Electrons at low energy are cheap. Good, use those. Each wall was a fact about a particular tool, and each was escaped by picking up a different tool. There are no more tools. There is one relation, and everything with a wavelength obeys it, and everything obeys it in the same way, which means that any limit we find from here on is not a limit on a technique, it is a limit on measurement itself. That distinction is worth taking seriously, because physics has a long and productive history of taking it seriously. There is a principle underneath the discipline, one that has been quietly doing more work than any particular theory, and I want to state it now so that it is in your hands before we need it. If a quantity cannot be measured, even in principle, physics does not get to talk about it. That sounds harsh. It has been extraordinarily useful. In the late 1800s, physics believed in the ether, a medium filling all of space, the thing that light waves were supposed to be waves in. And with the ether came the idea of an absolute velocity, your true speed, relative to the ether, whatever the local measurements said. The Michelson-Morley experiment went looking for it, found nothing, and Einstein's answer was not to hunt harder. His answer was to notice that if no experiment can determine your absolute velocity, then absolute velocity is not a physical quantity, and a theory that assigns you one is carrying something that does not exist. Take it out, and special relativity is what remains. The same knife cut away absolute simultaneity. There is no experiment that can establish whether two separated events happened at the same moment in any observer-independent sense. So there is no such fact. Not hidden from us. Not there. Both of those retirements felt like losses at the time, and turned out to be the exact opposite. Every time physics has thrown away an unmeasurable quantity, the theory that remained was simpler, stronger, and more predictive than the one it replaced. Keep that principle where you can reach it. We are going to hand it a much larger victim before the night is over. For now, we have our universal relation, and it has one more thing to tell us. Because there is a term we have ignored in every single calculation so far. Quietly, reasonably, on the entirely correct grounds that it was too small to matter. It is not too small anymore. The term we have been ignoring is gravity. That will sound like a joke if you have spent any time with particle physics, because gravity is famously, absurdly, insultingly weak. The electrical repulsion between two protons is something like 10 to the 36th times stronger than their gravitational attraction. A fridge magnet the size of a coin lifts a paperclip against the gravitational pull of an entire planet. When physicists calculate what happens inside a collider, they do not neglect gravity because it is difficult. They neglect it because including it would be like adjusting a national budget for the value of a single grain of rice. So gravity has never appeared in anything we have done tonight, and that was entirely correct, right up until it is not. Here is the piece of general relativity that matters. In Einstein's theory, space-time is not a stage that events happen on. It is a participant. It bends, stretches, and curves in response to what it contains. And crucially, what it responds to is not mass. It is energy, momentum, pressure, and stress, all of it taken together. Mass is one contribution among several, and it happens to be the dominant one for planets and stars, which is why we grow up thinking gravity is about mass. But a photon has no mass at all, and a photon still curves space-time because it carries energy. This is not an exotic reading of the theory. It is the plainest content of the field equations. Energy gravitates, all of it, always. Now look again at the master equation with that in mind. The energy we need is Planck's constant times the speed of light, divided by the distance we want to resolve. As the distance shrinks, the energy grows in exact proportion. And where does that energy have to be? Concentrated in the region we are trying to resolve. That is what probing a small region means. You deliver the probe's energy into that volume. So as we descend, two things happen at once, and they compound. The amount of energy goes up as 1 over the distance. The volume it is packed into goes down as the distance cubed. Multiply those together, and the energy density in the region climbs as the fourth power of 1 over the distance. Halve the target size, and the energy density goes up 16 times. Divide the target by 1,000, and the energy density goes up by a factor of 1,000,000,000,000. There is no scale at which a quantity growing like that can be safely ignored forever. Gravity is weak, but it is not zero, and it is being multiplied by something that is running away. And general relativity has been extremely clear since 1916 about what happens when you push energy density too far. Take a spherical object of some mass and shrink it while keeping the mass fixed. Nothing dramatic happens for a long time. The surface gravity climbs, the escape velocity climbs, and then you reach a particular radius at which the escape velocity equals the speed of light, and past that point nothing, no rocket, no light beam, no signal of any kind, can leave. That radius is called the Schwarzschild radius, and it is a beautifully simple thing. 2 times the gravitational constant times the mass, divided by the speed of light squared. Since we are only after an order of magnitude tonight, we will drop the 2 and say the critical radius is roughly the gravitational constant times the mass, divided by the speed of light squared. Inside that radius is an event horizon, not a surface, not a wall, a boundary in the geometry, past which every possible path leads inward. Whatever is in there is not hidden in the ordinary sense of being obscured. It is causally severed. No information from inside can ever reach anyone outside, ever, by any means. Now the piece that fuses the two halves of tonight together. Einstein's other famous equation says energy and mass are the same currency at a fixed exchange rate. Mass equals energy divided by the speed of light squared. Substitute that into the Schwarzschild radius, and you get the same statement in terms of energy. The critical radius is the gravitational constant times the energy, divided by the speed of light to the fourth power. Which means every concentration of energy, not just every mass, every energy, has a critical radius attached to it. Squeeze that energy inside that radius, and the region closes. And now watch the collision, because it is unavoidable. Our master equation says, to resolve a small distance, deliver a large energy into that small region. Small distance, big energy. The Schwarzschild relation says, a big energy has a big critical radius. So as we push the target distance down, the energy required goes up, and the critical radius of that energy goes up with it, while the region we are cramming it into is going down. Two curves, moving toward each other from opposite directions. They are going to meet. It is not a question of whether, it is arithmetic. Let me put you at the controls, because this is the moment. You are turning a dial. The dial sets the energy of your probe, and in front of you is an image of a region of space, and the image sharpens as you turn. Every increment of energy buys a little more detail. You go past the atom, and the lattice resolves into individual sites. Past the nucleus, and the proton resolves into hard little scattering centers. Past that, and structures nobody has names for begin to separate out of the blur. The dial has never lied to you. Turn and see more. It has been the deal your whole life. You keep turning, and somewhere, not with a bang, not with an error, just quietly, the image at the center stops sharpening. You turn further. The center goes dark, not blurry, dark, a small circular region of absolute nothing, and it is not that your instrument has failed, because the rest of the field is still perfectly crisp. You turn the dial harder, because that is what you have always done, and the dark region does not clear. It grows. That is the reversal, and it is the hinge of the entire video, so let me state it as plainly as I can. Above the crossing point, resolution is 1 over energy. More energy, smaller detail visible, the relationship we have followed all night. Below the crossing point, the probe energy has collapsed behind a horizon, and the size of that horizon is proportional to the energy. Resolution is now energy. More energy, bigger horizon, larger region hidden. The graph of what you can see against what you spend does not rise forever. It rises, it turns over, and it falls. And the peak of that curve is the finest view of the universe that anything, anywhere, is ever permitted to have. 2 clarifications before anyone objects, because both objections are good ones. The first is about shape. The Schwarzschild radius describes a nice round static mass, and a head-on collision of 2 ultra-relativistic particles is neither round nor static. Does the collapse argument survive that? It does, and the reason has a name. In 1972, Kip Thorne proposed what is called the hoop conjecture. A horizon forms when, and only when, you compress a mass into a region small enough that a hoop of the critical circumference could be slipped around it in every direction. It is a statement designed precisely for messy, non-spherical situations, and 2 particles meeting head-on at sufficient energy satisfy it just as surely as a collapsing star does. The second is about permanence. When I say a black hole forms, I do not mean a lasting object sitting in your laboratory. A horizon made at this scale would enclose about 1 Planck mass of energy, and by Hawking's mechanism, an object that small evaporates almost immediately, in something like 1 unit of Planck time, which is the shortest interval this whole framework allows anyone to speak about. The horizon flickers into existence and is gone. That does not help. It does not need to last. It only needs to exist during the measurement. because during the measurement is exactly when the information you are trying to collect is prevented from reaching you. The region does not have to stay hidden forever. It only has to be hidden while you are looking. For a sense of what is being demanded here, the energy density at that threshold is around 10 to the 96th kilograms per cubic meter. There is no honest comparison for that number. Take the entire mass of everything in the observable universe, compress it into the volume of a single atomic nucleus, and you are still short by roughly 60 orders of magnitude. Now, the natural response to this is to go looking for a loophole, and I want to close the obvious ones before we go on, because the strength of this argument is that it does not care about your cleverness. Could a better detector help? No. The problem is not on the detection side. The information about the hidden region is not faint, it is absent. Nothing carrying it ever left. Could a different particle help? No. We spent the whole of the last part establishing that every probe converges on the same energy wavelength relation. The horizon forms in response to energy, and it does not ask what the energy was made of. Could you use less energy and be more patient? Take many soft measurements and combine them? No. And this one is worth a sentence more. Resolution is set per interaction, by the wavelength of the individual quantum doing the scattering. 1 billion soft photons give you a very bright image, at the resolution of a soft photon. Statistics improve your certainty about what you have seen. They do not create detail the probes never carried. Could you come at it from many directions at once, so that no single beam is too energetic? That is the worst option of all. Converging beams concentrate energy in the target region more effectively, which is exactly the condition for collapse. You would be building the horizon faster. There is no escape, because the argument uses only two ingredients, and both of them are load-bearing walls of modern physics. Anything with a wavelength has an energy. Any energy gravitates. Which leaves exactly one question, and it is a question with a specific numerical answer. Where do the two curves cross? Finding where the two curves cross takes 3 lines of algebra, and I am going to walk you through them slowly, because I think it is worth seeing how little machinery this requires. There is no advanced mathematics here. There is nothing you could not have done at school. And what comes out the other end is one of the most consequential numbers anyone has ever written down. Line 1. Set the two conditions equal to each other. The region we are trying to resolve has some size, and we ask when that size equals the critical radius of the energy we are pouring into it. The size of the region equals the gravitational constant times the energy divided by the speed of light to the 4th. Line 2. We know what the energy has to be because the master equation tells us. It is Planck's constant times the speed of light divided by the size of the region. Substitute that in. On the right-hand side we now have the gravitational constant times Planck's constant times the speed of light divided by the size of the region, all divided by the speed of light to the 4th. Tidy up the speed of light. 1 factor on top, 4 underneath, leaves 3 underneath. And the size of the region has appeared in the denominator on the right, while sitting alone on the left, so multiply both sides by it. Line 3. What you are left with is the size of the region, squared, equals the gravitational constant times Planck's constant, divided by the speed of light cubed. Take the square root of both sides. The distance at which the two curves cross is the square root of the gravitational constant times Planck's constant, divided by the speed of light cubed. Stop and look at what is inside that square root, because the ingredient list is the most remarkable part of it. There is the gravitational constant, the strength of gravity, the number that tells you how much space-time bends per unit of energy. That came from general relativity. There is the speed of light, the conversion factor between space and time, the structure of the causal order. That came from special relativity. And there is Planck's constant, the quantum of action, the graininess that makes a photon a photon. That came from quantum mechanics. 3 constants. from three theories that were developed separately by different people to solve unrelated problems, and that have never been successfully combined into a single framework. And here they are, sitting inside one square root, producing a length. That is not a formula somebody constructed. It is a formula that fell out of asking a completely innocent question about microscopes. The number it produces is 1.616255 times 10 to the minus 35 meters. That is the Planck length. You will sometimes see it quoted as about 4 times 10 to the minus 35 meters instead. That is the same quantity written with Planck's constant rather than the reduced Planck constant. And the two differ by the square root of 2 pi, which for an argument that has been throwing away factors of 2 all night is not worth a second thought. There is one small footnote about precision that is more interesting than it sounds. 2 of the 3 constants in that expression are now exact by definition: the speed of light and Planck's constant. Only the gravitational constant is still measured, and it remains, by a wide margin, the worst known of the fundamental constants. We have it to about 5 significant figures, and independent laboratories using torsion balances have disagreed with one another by considerably more than their stated errors for decades. So the uncertainty in the Planck length is inherited entirely from our stubborn inability to weigh gravity properly. The floor of physical knowledge is fuzzy in the 5th decimal place, for the most mundane reason imaginable. Now let us try to feel the size of it, and let me be honest in advance that we will fail. A proton is about 0.84 femtometers across, around 8 times 10 to the minus 16 meters. The Planck length is smaller than a proton by a factor of about 5 times 10 to the 19, 20 orders of magnitude. Whatever intuition you have for the size of a proton, and you almost certainly do not have one, the Planck length is that far below it again. Try it as a scaling. Take a Planck length and blow it up until it is the size of a single atom. On that same magnification, how big is an actual atom? About 100 million times the width of the observable universe. Or count. The observable universe is roughly 9 times 10 to the 26th meters across. Divide by the Planck length, and you get about 5 times 10 to the 61. 5 followed by 61 zeros. That is how many Planck lengths it takes to span everything we can see, and it is a fair measure of the dynamic range that any final theory of physics has to cover in one piece. Or try it as a proportion, which sometimes lands when the raw exponents do not. The ratio between an ordinary atom and the Planck length is roughly the same as the ratio between the entire observable universe and a virus. An atom, to the Planck length, is a cosmos. I should also say clearly, since we are going to spend the rest of tonight refining it, what this number is not. It is not the size of anything. It is not a grain, or a pixel, or a smallest brick. Nothing has been measured to be 1 Planck length across, because nothing has been measured at that scale at all, and nothing ever will be. What we have derived is a limit on an operation, on the act of asking how far apart 2 things are, and getting an answer that could be checked. Keep that distinction sharp. Almost everything you will hear said about this number in casual conversation gets it wrong in exactly that one place, and the difference turns out to matter enormously. Now here is what I want you to actually sit with, because it is the thing that makes this number different from every other small number in science. Tonight we have watched the most extravagant machines our species has ever constructed fight their way down this ladder. Optical lenses to X-rays. X-rays to electron beams to a 2-mile linear accelerator, that to a 27-kilometer superconducting ring, cooled below the temperature of deep space, costing the better part of a decade and the wealth of a continent. All of that effort takes us from the scale of a person at about a meter down to 10 to the minus 20 meters. 20 orders of magnitude of progress for the entire history of observation. The Planck length is 15 more. And this is where it stops being a story about difficulty. If it were only difficulty, the correct response would be patience, a longer accelerator, a colder magnet, a richer century. Difficulty is what humans are for. But the argument we just walked through does not say that reaching it is hard. It says that arriving there destroys the thing you came to look at, using the same physics that got you down the ladder in the first place. The wall is not at the end of the road. The wall is made of the road. Nobody will ever measure a Planck length. Not with more money, not with better engineering, not in 10,000 years, not with technology we cannot imagine, not because we are small, but because the laws are consistent. And there is one last thing about this number that I find genuinely eerie. It was written down in 1899. In May of that year, Max Planck published the 5th installment of a series of papers on irreversible radiation processes, and in the final section, a short piece titled, in German, Natural Units of Measurement, he pointed out something aesthetic. If you take the gravitational constant and the speed of light and the new constant he had introduced in his radiation work, you can combine them to produce a unit of length, a unit of time, a unit of mass, and a unit of temperature, without reference to any human convention. No meters, no seconds, no kilograms, borrowed from a bar of metal in Paris. Just the universe's own numbers. His argument for their importance was, in his own words, that such units necessarily retain their meaning for all times and for all civilizations, even extraterrestrial and non-human ones. He was making a point about universality. He was not making a prediction. He could not have been. Quantum mechanics did not exist yet. General relativity would not exist for another 16 years, and the idea that space-time might have a smallest meaningful scale was not a thought anyone was capable of having. He assembled the number because it was elegant, and then he moved on. The other quantities in his little table are worth knowing, since they are all the same statement in different currencies. The Planck time, 5.39 times 10 to the minus 44 seconds, is how long light takes to cross a Planck length, and by the same arguments, the shortest interval, about which the word duration can carry a checkable meaning. The Planck temperature is about 1.4 times 10 to the 32nd Kelvin, and the Planck mass, which we will come back to shortly, is 2.18 times 10 to the minus 8 kilograms. 127 years later, we now have reason to believe that one of the numbers Max Planck wrote down for the sake of tidiness marks the boundary of what can be known. Which raises the obvious next question. If we cannot get there, how far away is it, in the only currency this story has ever accepted? What would it cost? The master equation has been quoting us prices all night, so let us ask it for the last one on the list. Put the Planck length in as the distance we want to resolve, and out comes the energy required. It is about 1.22 times 10 to the 19th giga-electron volts. Written out, that is roughly 12 billion electron volts. This quantity is called the Planck energy, and it is the price of the last ticket. Here is the first, genuinely disorienting thing about it. As a quantity of energy, in ordinary human terms, it is nothing special at all. 1.2 2 times 10 to the 19 GeV works out to about 2 billion joules. 2 billion joules is roughly 540 kilowatt hours. Call it a couple of weeks of electricity for an average household. It is the energy in 15 or 20 litres of petrol. It is a large lightning strike. It is, in the scheme of things people casually consume, unremarkable. The problem has never been the total. The problem is where it has to go. You have to put all of it on a single quantum. One particle, carrying a fortnight of a family's electricity supply, all by itself. Every joule of it in one indivisible parcel, because the master equation is about the wavelength of an individual probe, and 1 billion soft probes will not do the work of one hard one. Expressed as a mass, that same energy is the Planck mass, 2.18 times 10 to the minus 8 kilograms. And this is the strangest quantity in the entire Planck family, because unlike the length and the time, it is not absurd. 22 micrograms. That is a fleck of dust. It is roughly the mass of a small grain of sand, or a single eyelash, or an eyebrow hair. It is a thing you could hold if you could see it, and it would weigh nothing to you at all. And it is about 13 billion times the mass of a proton. That contrast is a message, and the message is about how weak gravity is. Nature's natural unit of mass, the one built from gravity and quantum mechanics and relativity together, sits absurdly far above the mass of anything we call a particle, and comfortably within the range of things you could put on a laboratory balance. The reason the Planck length is so unreachably small is the same reason the Planck mass is so weirdly large. Gravity is feeble, and it takes a preposterous concentration of anything before it starts to matter. It is worth asking whether nature ever manages this concentration on its own, since nature is not constrained by construction budgets. The most energetic single particles ever detected are ultra-high energy cosmic rays, and they are genuinely astonishing. The record holders carry more than 3 times 10 to the 20th electron volts, which is a single subatomic particle arriving with the kinetic energy of a well-struck tennis ball. Nobody knows for certain what accelerates them. And they are still 100 million times short of the Planck energy. And that is before you account for the fact that what matters in a collision is the energy in the center of mass frame, not the lab frame, which for a cosmic ray hitting a stationary atmospheric nucleus knocks the useful figure down by a further enormous factor. The universe, in other words, is not running this experiment for us anywhere we can see. Not in the atmosphere, not in a supernova, not in the jets of an active galaxy. The only place the Planck energy was ever routinely available was the first fraction of a second after the Big Bang, and the record of that is smeared across the sky as microwave radiation, not resolvable as an image of anything. Now let us do the fun part and build the machine. The Large Hadron Collider accelerates protons to 6.8 tera-electron volts using a ring 27 kilometers around. We want 1.22 times 10 to the 19th GeV. That is a factor of roughly 2 times 10 to the 15 higher. Call it 1,000 million times more energy per particle. Bending charged particles in a circle takes magnetic field, and for a given field strength, the energy you can reach scales with the radius of the ring. So let us make the friendliest possible assumption and simply scale the LHC's circumference by the same factor, 27 kilometers, multiplied by 2 times 10 to the 15. The answer is about 5 times 10 to the 16 kilometers. That number means nothing in kilometers, so convert it. 1 light year is about 9.5 trillion kilometers. Our ring comes out at roughly 5,000 light years around. Let me lay that beside things you can hold in your head. The nearest star to the Sun, Proxima Centauri, is 4.2 light years away. So this accelerator would be more than 1,000 times the distance to the nearest star. You would need to lay the entire journey to Proxima Centauri, end to end, more than 1,000 times just to complete one lap. The solar system, generously defined all the way out to the icy shell of the Oort cloud, is a couple of light years across. The machine would be thousands of times larger than the whole solar system, planets, comets, and all. The disk of our galaxy is about 100,000 light years wide. This device would span a few % of the Milky Way. You could not see it from any single vantage point. Light would take 50 centuries to travel from one side of it to the other. A signal sent to check that the far end was ready would be answered by a civilization 5,000 years further along than the one that asked. Stand next to it, if you can. There is a curve of beam pipe running off in both directions, so gently bent that it looks perfectly straight, threading through the dust lanes of a spiral arm and out past a scattering of unfamiliar stars. Walk along it. Keep walking. A human lifetime at walking pace would not get you past a section you could measure as a fraction of a percent of the whole. There is no control room, because there is no vantage from which the thing could be controlled. Whatever built this did not build it in a lifetime, or a dynasty, or a civilization, and it is still one machine, one ring, one experiment, running one collision. And I have been generous throughout. That scaling ignores synchrotron radiation, which bleeds energy out of any charged particle forced to travel in a curve, and gets catastrophically worse at high energy. It ignores every limit on magnet strength and beam stability, and vacuum quality. It assumes the entire structure could be built and held in alignment across 5,000 light-years, while the galaxy rotates underneath it. A real machine would be far worse than this fantasy. This is the optimistic version. Now here is the turn, and it is the reason we did this calculation at all. Everything I have just described sounds like an engineering problem, an absurd, extravagant, wildly impractical engineering problem, but an engineering problem, the kind of thing you could imagine a patient enough species solving in some distant future, the way we solved the 27-kilometer version. That is the wrong conclusion, and it is precisely the wrong conclusion this number tempts you into. The galaxy-sized accelerator would not work. Not because it is too small, not because the magnets would fail or the alignment would drift, because if you built it and switched it on and brought two protons together at the Planck energy, the collision would make a horizon. The energy required to resolve a Planck length is exactly the energy that closes a Planck length region behind an event horizon. You would spend 5,000 light-years of machine and receive, as your output, a black hole. Not an image of anything, a very small, very brief black hole which would evaporate immediately, telling you nothing about the region you were trying to inspect. Earlier tonight, I gave you a phrase to hold. When you cannot make something out, bring a brighter lamp. This is the brightest lamp the laws of physics will ever permit anyone to build, and it does not illuminate the room. It puts a hole in it. That is the difference between too expensive and impossible, and everything about tonight turns on it. The wall we have found is not a budget line. There is no future, no technology, no civilization, no amount of time for which this becomes a solved problem. Which is exactly the point at which a careful person should get suspicious, because everything I have shown you so far rests on one chain of reasoning. It is a clean chain, but it is one chain, and in theoretical physics, a single elegant argument that proves something can never be done has a truly dismal historical record. So let us throw it away. Let us start again from a completely different place, with different physics, a different century, and a different question, and see where we end up. There is a reason physicists do not fully trust a result until it has been derived twice, from two directions, by two methods that have nothing to do with each other. A single argument, however clean, carries all of its assumptions in one bundle. If any one of them is wrong, a step that seemed innocent, a term dropped too early, a piece of physics applied outside its range, then everything downstream of it is wrong too, and you may not find out for 50 years. The history of the subject is littered with beautiful proofs of impossibility that turned out to have a hidden door in them. Von Neumann proved that hidden variable theories of quantum mechanics were impossible, and the proof stood for 3 decades before John Bell pointed out that one of its assumptions was unreasonably strong. So let us do the honest thing, and abandon the argument we spent the last 4 parts building. Forget black holes. Forget the Schwarzschild radius. Forget general relativity, almost entirely. We are going back to 1927 and starting again from quantum mechanics. Werner Heisenberg introduced his uncertainty principle with a thought experiment about a microscope, and it is worth rebuilding from the ground up, because it is the cleanest derivation in physics, and almost nobody sees it anymore. You have an electron. You know it is somewhere inside a small region, and you would like to know exactly where. So you do the only thing anybody has ever done. You shine light into the region and catch what scatters off. Now apply the rule we established in the very first part of tonight. The precision with which you can locate the electron is limited by the wavelength of the light you used. A long wavelength washes over the electron and gives you a vague answer, so the uncertainty in position is roughly the wavelength of your probe. If you want a better answer, you need a shorter wavelength. And by de Broglie, or by Einstein, they agree. A shorter wavelength means a higher momentum photon. Specifically, the momentum of the photon you need is roughly Planck's constant divided by the position uncertainty you are willing to accept. Want to halve the uncertainty, double the photon momentum. But a photon is not a passive observer. When it bounces off the electron, it hits it. It transfers momentum, and it transfers an amount of the same order as the momentum it was carrying, because that is what bouncing means. So the electron, which may have been sitting quite still, is now moving, and you do not know precisely how fast, because you do not know precisely which way the photon scattered. The uncertainty you have introduced into the electron's momentum is therefore about equal to the photon's momentum, which was Planck's constant divided by the position uncertainty. Rearrange that one line, and you have it. The uncertainty in position multiplied by the uncertainty in momentum is approximately Planck's constant. That is Heisenberg's principle, and notice that it was not postulated. It was derived from the physics of what a measurement actually is. The trade-off is not mystical. It is the direct consequence of having to hit something in order to see it. Everything up to this point is 1920s physics, and every physicist alive accepts every step of it. It is worth knowing that even this derivation had to be corrected. Heisenberg's original presentation leaned heavily on the disturbance caused by the collision, the photon knocking the electron about, and Niels Bohr, reading a draft, told him bluntly that he had got the emphasis wrong. The uncertainty, Bohr argued, is not fundamentally about a clumsy measurement jostling a definite value. It is about the wave nature of both the probe and the target. A wave confined to a small region simply does not have a single well-defined wavelength, and therefore does not have a single well-defined momentum, whether or not anybody looks. The two men argued about it for weeks in Copenhagen in the spring of 1927, and Heisenberg added a note to his paper acknowledging Bohr's point. The reason I mention this is that Bohr's correction makes the principle stronger, not weaker, and it does not touch the calculation we are about to do. Whether you read the microscope story as a description of a real disturbance or as a heuristic for an underlying wave property, the arithmetic comes out the same, and the extra term we are about to add attaches to it either way. Now we add one thing. Exactly one. The thing Heisenberg had no reason to include, because in 1927 nobody was thinking about gravity in the same breath as an electron. The probe photon has energy, and energy, as we established, gravitates. If that still feels like a technicality, remember that it was tested and confirmed more than a century ago in the other direction. In 1919, Arthur Eddington's expeditions photographed stars during a total solar eclipse and found their apparent positions shifted because starlight passing near the sun had been bent by the sun's gravity. Light responds to gravity. Einstein's theory also says the relationship runs both ways, that light, carrying energy, is itself a source of gravity. We have never measured that second half directly, because the effect for any beam we can produce is beyond ridiculous. But it is not an optional extra bolted onto the theory. It is the same equation read from the other side. If it were false, general relativity would be false. So let us work out how much. Give the photon a frequency. Its energy is Planck's constant times that frequency. Convert to an effective mass by dividing by the speed of light squared. That is a real quantity. The photon has no rest mass, but it has an energy, and that energy sources a gravitational field just as surely as a rock does. As the photon comes in toward the electron, that effective mass pulls on the electron. Newton is more than good enough for an estimate. If the interaction happens over some characteristic distance, then the gravitational acceleration of the electron toward the photon is the gravitational constant times the photon's effective mass, divided by that distance squared. Write out the effective mass, and you get the gravitational constant times Planck's constant times the frequency, divided by the speed of light squared, divided by the distance squared. The photon is not going to hang around. It arrives at the speed of light and leaves at the speed of light, so the interaction lasts about as long as it takes light to cross the region. The distance divided by the speed of light. Now use the most schoolroom formula in all of physics. An object under constant acceleration, starting from rest, moves a distance of 1/2 times the acceleration times the time squared. Substitute in the acceleration we just derived, and the time we just derived, and simplify. Something remarkable happens when you do. The distance cancels completely. It appeared squared in the denominator of the acceleration and squared in the numerator of the time, and the two annihilate each other. That is worth pausing on. It means the amount by which the probing photon gravitationally displaces the electron does not depend on how close the photon passes. Near or far, the effect is the same. There is no standing back from this one. You cannot arrange the geometry to make it small. What you are left with is the displacement equals the gravitational constant times Planck's constant times the frequency divided by the speed of light to the 4th power. Tidy it into the language of the rest of the argument. A photon's energy is its momentum times the speed of light, so Planck's constant times the frequency is just the momentum times the speed of light. Substitute that, cancel 1 power of the speed of light, and the displacement becomes the gravitational constant times the photon's momentum divided by the speed of light cubed. And we already established that the photon's momentum is what sets the uncertainty in the electron's momentum. So finally, there is an additional uncertainty in the electron's position, and it is equal to the gravitational constant times the uncertainty in momentum divided by the speed of light cubed. Look at the shape of that and compare it to Heisenberg's term. Heisenberg's uncertainty in position is Planck's constant divided by the uncertainty in momentum. Momentum in the denominator. As momentum uncertainty goes up, position uncertainty goes down. That is the familiar trade. Pay in momentum, buy position. The gravitational term has the uncertainty in momentum in the numerator. As momentum uncertainty goes up, position uncertainty goes up too. They pull in opposite directions, in the same measurement, using the same photon. The first term is the reason you use a harder probe. The second term is the price of having used one. And the second term was always there. It has been sitting inside every measurement anyone has ever made, from Davison and Germer's nickel crystal to the Higgs discovery, quietly contributing an amount so unimaginably small that no experiment could ever have noticed it. The gravitational constant in the numerator and the speed of light cubed in the denominator make it, at ordinary energies, one of the tiniest quantities in physics. But it does not stay tiny, because it grows with exactly the thing we keep increasing. Add the two effects together. Write the total position uncertainty as Heisenberg's term plus the gravitational term. That expression has a name, the generalized uncertainty principle, and we now have it in front of us, assembled out of nothing but a photon, an electron, Newton's law of gravity, and a formula about accelerating objects that you learned when you were 15. A word about how crude that derivation was. because I would rather say it than have you suspect it. We used Newtonian gravity for a photon, which is formally wrong. We used a schoolroom kinematics formula for a situation with no constant acceleration. We ignored every numerical factor. A proper treatment inside a full theory would put a dimensionless number in front of the gravitational term. Physicists usually call it beta, and different underlying theories predict different values for it. Nobody can tell you what beta is, because telling you would require the theory of quantum gravity we do not have. But look at what the crudeness can and cannot damage. It can change the size of the effect by some factor. It cannot change the sign, and it cannot change which way the term runs with momentum, because that comes from the structure of the physics and not from the arithmetic. More energetic probe, stronger gravitational pull, larger displacement. And as we will see in a moment, the sign and the direction are the entire result. That is why a calculation this rough is taken this seriously. We have not yet asked what it does. I have deliberately not told you where it lands, and if you are ahead of me, hold on to your suspicion for one more part, because I want us to solve it properly rather than guess. There is a function on the table with two competing terms. One falls, one rises. What we do next is the most ordinary thing in mathematics. We find its minimum. Picture the graph, because the answer is visible in the shape before you do any algebra at all. Along the bottom, the uncertainty in momentum, how hard you are hitting the electron, how much of its motion you are willing to scramble in exchange for knowing where it is. Up the side, the uncertainty in position, how well you actually end up knowing where it is. Low on the vertical axis is good. Low means precise. Draw Heisenberg's term first. Position uncertainty equals Planck's constant divided by momentum uncertainty. That is a hyperbola. It comes down steeply from the top left and flattens out as it runs to the right, forever approaching the horizontal axis without ever touching it. This is the curve every physicist carries in their head, and its message is straightforward and encouraging. There is no limit to how precisely you can locate something. You just have to be willing to pay, and the payment is in momentum, and you can always pay more. Now draw the gravitational term on the same axes. Position uncertainty equals the gravitational constant times momentum uncertainty divided by the speed of light cubed. Momentum on the top. That is a straight line, rising from the origin. Its slope is fantastically shallow. The gravitational constant divided by the cube of the speed of light is about 2 times 10 to the minus 52 in standard units, which is a slope so gentle that across the entire range of every experiment ever performed, the line is indistinguishable from the horizontal axis. Now add them, and follow the sum from left to right. At the left, the hyperbola is enormous, and the line is nothing. The sum is essentially the hyperbola. It plunges. Every increase in momentum buys you a large improvement in position, exactly as advertised. Further right, the hyperbola has flattened out and is contributing very little. The line, meanwhile, has been quietly climbing the whole time. The sum stops falling. It levels off. Further right still, the hyperbola is negligible and the line is all that is left. The sum rises. Your position uncertainty is getting worse, and getting worse in proportion to how hard you are trying. Between the falling part and the rising part there is a minimum, a single point, at a single value of momentum, where the total position uncertainty is as small as it is ever going to get. That is the whole result, in a picture. Beyond a certain momentum, hitting harder makes you blinder. Now find the minimum properly. To locate the bottom of a curve, you differentiate and set the result to 0, which here gives minus Planck's constant, divided by the momentum uncertainty squared, plus the gravitational constant, divided by the speed of light cubed, equals 0. Rearranged, the momentum uncertainty squared equals Planck's constant times the speed of light cubed, divided by the gravitational constant. Take the square root, and you have the momentum at which the curve bottoms out. That quantity has a name. It is the Planck momentum. And now substitute it back into the relation to get the actual value of the minimum, the smallest position uncertainty that this universe permits. When you do the substitution, both terms come out identical, which is a small piece of mathematical elegance in itself. At the bottom of the curve, the quantum cost and the gravitational cost are exactly equal. Add them and you get twice the square root of the gravitational constant times Planck's constant divided by the speed of light cubed. That expression should look extremely familiar. It is the Planck length, again, to within a factor of 2. Sit with that for a moment, because I do not think it can be overstated. In the first half of tonight, we took general relativity, considered the collapse of concentrated energy into a black hole, asked when a region would hide itself behind a horizon, and got a length, the square root of the gravitational constant times Planck's constant over the speed of light cubed. Just now we took quantum mechanics, considered a photon bouncing off an electron, added the gravitational tug of the photon on its target, minimized the resulting function, and got a length, the square root of the gravitational constant times Planck's constant over the speed of light cubed. Those two arguments share nothing. The first is about horizons, escape velocities, and the geometry of collapsing energy. It never mentions measurement precision or a trade-off. The second is about a single photon nudging a single electron, and it never mentions horizons, gravitational collapse, or black holes at all. Nowhere in that derivation does anything collapse. One of them is a story about the largest objects in the universe. The other is a story about the smallest possible interaction between two particles. They are not two versions of the same calculation. They are two calculations, and they returned the same number. That is what physicists mean when they say a result is robust. It is not that the argument is airtight. We have been dropping factors of 2 all night. It is that the conclusion survived being derived by someone who was not trying to derive it. If there were a mistake in the black hole argument, it would have to be a mistake that happens to be replicated exactly by a completely unrelated piece of reasoning about photon recoil. That is not how mistakes usually behave. It is also worth noticing that this modified relation, if it is right, does not politely confine itself to the Planck scale. A term added to the uncertainty principle propagates into everything built on top of the uncertainty principle, which is most of quantum physics. It changes how you count the available quantum states in a volume, which feeds into statistical mechanics and thermodynamics. It alters the endgame of black hole evaporation. In several treatments, a shrinking black hole does not disappear completely, but stalls at a Planck scale remnant, because the same flaw that stops you resolving a small region stops the whole from becoming one. Some versions even nudge the maximum mass a white dwarf can carry before it collapses. None of these consequences is anywhere near measurable today. All of them are places where, in principle, the flaw could eventually leave a fingerprint on physics we can actually reach. This convergence has a history, and it is a slightly lonely one. The first person to work it out carefully was not a famous physicist. C. Alden Mead was a chemist at the University of Minnesota, and in 1964 he published a paper in Physical Review with the plain title Possible Connection Between Gravitation and Fundamental Length. In it he analyzed hypothetical experiments in detail and concluded that gravitational effects make it impossible to measure a particle's position to better than about 10 to the minus 33 centimeters, which, in the units of the day, is the Planck length. He went further and argued that any attempt to formulate a theory with a fundamental length while leaving gravity out of it may simply be impossible. Mead spent years trying to get the paper published. The physics establishment of the time regarded it as not obviously interesting. Then the idea arrived independently from somewhere else entirely. In 1989, Daniele Amati, Marcello Ciafaloni, and Gabriele Veneziano published a paper with a question for a title: Can spacetime be probed below the string size? They were studying what happens when strings collide at extremely high energies, and they found that the resolution improves with energy up to a point, then reverses, that beyond a critical scattering angle the effective distance starts increasing again, departing from the ordinary position-momentum relation, and that in no case does the resolution get smaller than the string length. That is the same turning curve, arrived at from inside a theory of quantum gravity, rather than from outside it. 10 years later, Fabio Scardilli showed that you could get the generalized uncertainty principle from a micro-black hole thought experiment, using nothing more than Heisenberg's principle and the Schwarzschild radius. No string theory, no loops, no commitment to any program at all. And in 1995, Luis Garay published a review surveying the whole landscape, the different, mutually incompatible approaches to quantum gravity that were then in play, and what, if anything, they agreed about. His conclusion was that the existence of a fundamental scale, a lower bound on any output of a position measurement, appears to be a model-independent feature of quantum gravity. Approaches that agree about almost nothing else agree about this. He added the consequence in one dry sentence: classical notions such as causality or distance between events cannot be expected to be applicable at that scale, and must be replaced by some other, as yet unknown, structure. Let me be careful about what the agreement licenses, because I do not want to oversell it. These arguments do share one assumption, and it is the only one. They both assume that quantum mechanics and gravity apply to the same object at the same time, that the photon in your measurement is simultaneously a quantum thing with a wavelength and a gravitating thing with an energy. If that assumption is false, both arguments collapse together. But nobody has any idea how it could be false. There is no version of physics on the table in which some objects have wavelengths and do not gravitate, or gravitate and do not have wavelengths. To escape this conclusion, you would have to break one of the two most thoroughly tested theories in the history of science, in a way that leaves all of its successful predictions intact. So we have our wall, twice over, which finally lets us ask the question we have been circling since the first minute, and it is not the question you might expect. The question is not what is down there. The question is what down there could possibly mean. Let us step back for a moment and put the pieces on the table together, because we have covered a great deal of ground, and it is worth seeing the whole shape at once before we push on. We started with the only method of seeing anyone has ever had: scatter something off a thing and read what comes back. That method has a rule. The wave must be no larger than the feature, and the rule has a price, which is that shorter waves cost more energy. We followed the price down through 5 orders of magnitude of human ingenuity, from lenses, to X-rays, to electron beams, to a 2-mile LINAC, to a 27-kilometer ring, and it was paid every time. Then we noticed that energy gravitates, and that the price rises faster than the region shrinks, and that the two facts collide at a specific distance, beyond which more energy buys a bigger horizon rather than a smaller detail. Then we threw all of that away and rebuilt the argument from a photon nudging an electron, and got the same distance back. 1.6 times 10 to the minus 35 meters. 2 roads, 1 wall. So now, what do you build a theory out of if you cannot build it out of distances? That question is not rhetorical. It is the working problem of an entire field, and there are 2 serious, decades-old programs attacking it from opposite directions. Both are speculative. Neither has been tested. I am going to describe them honestly, which means describing their difficulties too. The first approach says, stop using point-like probes. Every argument tonight has assumed that what you send in is, in principle, a point, an electron, a photon, something with no size of its own, whose resolving power is set entirely by its wavelength. String theory throws that away. Its fundamental objects are not points but one-dimensional extended things, and their characteristic size is of order the Planck length. The consequence is immediate. An extended probe cannot resolve structure finer than itself, in the same way that you cannot feel the grain of a piece of paper through a boxing glove. But the interesting part is not the geometric obviousness. It is what happens when you try to force the issue. With a point probe, more energy means shorter wavelength means finer resolution. With a string, more energy does something else. The extra energy goes into exciting the string's vibrational modes, making it wobble in more complicated ways. And a more excited string is a physically larger object. It spreads. So pushing harder does not sharpen your instrument. It inflates it. There is a scale at which the two effects balance, and below that scale, the harder you push, the coarser your view becomes. You have heard that sentence before tonight, in two other contexts. Here it arrives from inside a theory's own dynamics, rather than being imposed from outside, and it produces its own version of the uncertainty relation with the same falling plus rising structure and the same turning point. There is a second result that string theorists tend to find more persuasive than the first, and it is worth stating because it is genuinely surprising. String theory was set up as a quantum theory of vibrating objects. Nobody put gravity into it. But when you take the low energy limit, when you zoom out and ask what the theory looks like at scales much larger than a string, the consistency conditions on how a string propagates turn out to require that the background spacetime satisfies Einstein's field equations. General relativity is not an ingredient, it is a consequence. A theory built to make one quantum object consistent contains, hiding in its long-distance behavior, the whole of Einstein's theory of gravity. The second approach goes the other way. Instead of putting a new kind of object onto a smooth background, loop quantum gravity refuses to assume the background at all, and applies quantum mechanics directly to geometry itself. The states of that theory are called spin networks. Picture a graph, nodes connected by links, each carrying a quantum number. In this framework, a link corresponds to a quantum of area, and a node to a quantum of volume. Space is not a smooth container that this network sits inside. The network is what space is. Geometry is a property of the graph, not of a stage the graph is drawn on. In 1995, Carlo Rovelli and Lee Smolin computed the spectra of the area and volume operators in this framework and found something remarkable. They are discrete. The possible values of area come in a spectrum with a smallest non-zero step, of order the Planck length squared, around 10 to the minus 70 square meters. On this picture, you cannot have half of the smallest area any more than you can have half a photon. Try to hold the two pictures side by side for a moment, because they are the two best answers anyone has. In the first, you are pressing a probe against the fabric of things and feeling it widen under your hand. You lean harder, and it spreads. You lean harder still, and it spreads more, and the sensation is of pushing against something that answers force by growing softer and broader until the harder you press, the less you can feel. In the second, there is nothing to press against. There is a lattice of relations, nodes joined by links, quantities of area and volume distributed across a graph, and you go looking for the space between two adjacent nodes, the little gap, the interval where you expect distance to live, and there is nothing there, not empty space, not a gap too small to measure. The question has nothing to attach to, the way asking what is north of the North Pole has nothing to attach to. The words are all grammatical, and the question does not exist. Now the honest part, because both of those pictures come with problems, and a channel that skipped them would be doing you a disservice. The first problem belongs to the whole idea of a minimum length, not to either theory. A length is not a relativistically respectable thing to have. If I measure a fundamental length of 1.6 times 10 to the minus 35 meters, and you fly past me at high speed, special relativity says you should measure it Lorentz contracted, smaller than the supposed minimum. A fixed smallest length picks out a preferred frame, and preferred frames are exactly what relativity abolished. There are two ways out. Either the Planck length is not a length between points at all, but a bound on measurement outcomes, which is the reading I have been careful to use all night, or the symmetry structure of spacetime is itself modified at high energy, which is the research program called doubly special relativity, in which the Planck energy joins the speed of light as a second invariant that all observers agree on. That program has real difficulties of its own, including the awkward question of what happens to a football whose total energy comfortably exceeds the Planck energy, and which does not appear to be forbidden. The second problem is that string theory, which gave us one of the original arguments for a minimum length, also supplies the sharpest counterexample to it. In 1995, Stephen Schenker pointed out that D-branes, extended objects discovered during string theory's second revolution, can probe distances shorter than the string length, by a factor that depends on the string coupling. If the coupling is weak, a d-particle probe resolves structure below the supposed flaw. So the minimum length in string theory is not absolute. It depends on what you probe with. This does not touch the black hole argument, which is about horizons rather than probes, but it does mean that anyone who tells you flatly that string theory predicts a minimum length is going further than the theory does. The third problem lives inside loop quantum gravity. The area and volume operators have discrete spectra. That much is a theorem. But those operators are not gauge invariant in the full theory, and whether their discreteness corresponds to something a physical observer could actually measure, rather than being an artifact of a particular technical choice, has been disputed at length, most prominently by Bianca Dittrich and Thomas Tiemann. The granularity is real inside the formalism. Whether it is real in the world is not settled. And the fourth problem is the largest. There is no evidence, none. That is not for want of trying, and the attempts are more ingenious than you might expect. The trick is to look for the shadow of Planck scale structure in something we can actually observe, some effect that accumulates over enormous distances or enormous times until it becomes visible. The best of these involves gamma-ray bursts. If space-time is granular, some models predict that photons of different energies travel at very slightly different speeds through it. Over a few meters, that is nothing. Over billions of light-years, it might add up. In 2009, the Fermi Gamma-Ray Space Telescope observed a burst catalogued as GRB 090510 from a source at a redshift of 0.9, light that had been traveling for something like 7 billion years. Among the photons was one carrying 31 giga-electron volts, and it arrived 0.829 seconds after the burst trigger. If high-energy photons were being slowed by a granular spacetime, that photon should have lagged further behind. It did not. The result excluded a linear variation of light speed with energy right down to, and slightly past, the Planck scale itself. The second attempt was built here on Earth. Craig Hogan argued that if the universe has a holographic information limit, positions should suffer a tiny random jitter, wandering by about a Planck length every Planck time, which would show up as a very specific kind of noise in a sufficiently sensitive interferometer. Fermilab built a machine for the purpose, the holometer, a pair of interferometers with 39-meter arms, designed to do nothing but listen for that hiss. In December 2015, after a year of data, it reported no detection, excluding Hogan's model at 4.6 sigma. Both null. And it is worth being precise about what null means here. Neither result contradicts anything in the arguments we have built tonight. Those arguments predict a wall at 10 to the minus 35 meters, not a signal at 10 to the minus 19. What the null results kill are specific optimistic models in which Planck scale structure leaves a large, accumulating fingerprint at accessible scales. The wall itself is untouched and also untested, and everyone in the field knows it. I want to close this part with the version of all this that you have probably heard somewhere else, because the correction is more interesting than the claim. You will find it said, frequently and confidently, that the Planck length is the pixel size of reality, and therefore evidence that we are living in a simulation. The reasoning is that a rendered world would need a finite resolution, and here is a finite resolution. It is wrong in a specific and instructive place. The arguments we did tonight do not produce a grid. They produce a bound on measurement outcomes, a floor under the answers, not a lattice of locations. And a lattice is exactly the thing that cannot be right, for the reason we just covered. A grid with a fixed spacing would be contracted by a moving observer and would single out a preferred frame. Whatever is underneath, it is not graph paper. There is also the small matter that nothing has ever been measured at this scale, so there is no observation of a pixel because there has been no observation at all. The related claim that the holographic principle proves the universe is a rendered display does the same thing with a different result. The holographic bound is real physics, and we will come back to it. It says the information content of a region scales with its surface area rather than its volume. It says nothing whatsoever about intent, computation, or a machine somewhere doing the computing. The word encoded is carrying the entire argument, and it is a word we chose. The one part of this story that deserves respect is the part I just told you about the holometer, and it deserves respect because of how it ended. Around 2009, there were widely circulated reports that a gravitational wave detector in Germany, GO 600, was seeing unexplained noise that might be exactly this holographic jitter. It was speculative, it was exciting, and instead of remaining a talking point, someone made it precise enough to test, and then built a machine to test it. The answer came back, no, that is not a failure. That is the only procedure anyone has ever found that reliably separates a good idea from a beautiful one. Which brings us, finally, to the question we have been holding since the first minute. Not what is smaller than the Planck length. Something harder. I promised at the beginning that by the end you would know exactly what fails. So let me answer it plainly, and then spend the rest of our time together on what the answer costs. Nothing breaks at the Planck length, in the sense that most people imagine. The laws do not stop working. There is no point at which general relativity throws up its hands or quantum mechanics returns an error. Both theories will happily accept a distance of 10 to the minus 50 meters and give you an answer, calmly and without complaint. The equations are perfectly well behaved all the way down. What breaks is something quieter and much worse. What breaks is the operation. The procedure that gives the word distance its meaning. Send something in, catch what comes back, compare, stops returning answers. And it does not stop for a practical reason. It stops because the two theories, applied together and taken seriously, arrange for it to stop. General relativity says the energy you need to look that closely will hide the region behind a horizon. Quantum mechanics, with gravity included, says the precision you are chasing turns around and degrades. Two verdicts, one sentence. So when we say physics breaks apart beyond the Planck length, we do not mean that the rules break. We mean that beyond that scale, the rules stop making statements that could ever be checked by anyone, anywhere, by any method. And that is not a small distinction, because of a principle we picked up earlier tonight and set down carefully for later. If a quantity cannot be measured, even in principle, physics does not get to talk about it. That rule has never once been kind. It took the ether. There was a medium filling all of space. It had properties Serious people spent careers on it, and when it turned out that no experiment could detect motion relative to it, the correct response was not to build a better detector. It was to notice that the thing had no observable consequences and remove it. It took absolute simultaneity, the perfectly obvious idea that two events either happen at the same moment or they do not. No experiment can settle that for separated events, and so there is no fact about it. Not a fact hidden from us. No fact. It took absolute rest and absolute velocity, and the notion of a universal present sweeping through the cosmos. Each of those was an approximation that worked beautifully at ordinary scales and quietly failed underneath. Each retirement felt like a loss and turned out to be the doorway to a better theory. Now look at what the same rule is pointing at this time. It is not a frame of reference. It is not an invisible fluid. It is the smooth, continuous, infinitely divisible space-time that you are lying in right now. The thing that makes the word between mean something. The thing that lets you say your hand is a certain distance from the wall and lets that statement be true. Every equation in physics is written on top of that continuum, including, and this is the part that has kept people up at night for 60 years, including the two equations we use tonight to prove that it cannot be probed. General relativity is a theory of a smooth manifold. Quantum field theory is written on a smooth background. We took those two theories, applied them to a measurement, and they told us in unison that the smoothness they are built on cannot be verified below a certain scale. The most successful descriptions of reality ever constructed appear to contain, inside their own logic, a proof that the arena they describe is not what they say it is. There are three ways to respond to that, and honest physicists hold all three. I am going to lay them out rather than choose, because I do not think anyone has earned the right to choose yet. The first response is the strict one. If it cannot be measured, it is not there. The continuum is a convenient fiction that does excellent work above the Planck scale and has no content below it, in exactly the way the ether had no content. On this reading, the job now is to find the variables that are measurable and build the theory out of those. And the fact that we cannot yet imagine what such a theory looks like is a fact about us. The second response resists. Unmeasurability is a fact about instruments, and instruments are physical objects with physical limitations. It does not follow that the world lacks structure where we cannot look. Perhaps there is perfectly definite geometry down there, exactly as smooth as it appears in the equations, and we are simply and permanently barred from checking. The uncomfortable consequence is a theory whose lowest layer is untestable in principle, which many physicists regard as no longer being physics at all. The third response dissolves the question, and it is the one I find most quietly unsettling, because it is the most familiar. Consider temperature. Temperature is real. You can feel it, measure it, build engines on it, and be killed by it. And temperature is not fundamental. It is a statistical property of the motion of enormous numbers of molecules. Now ask, what is the temperature of a single molecule? The question is not hard. It is not unanswered. It is malformed. Temperature is not the kind of thing that exists for one molecule, and the fact that it stops being defined at small numbers is not a limitation of thermometers. If space-time is emergent in that sense, if geometry arises from something else, some structure of relationships or entanglement or information that is not itself geometric, then asking what distance means below the Planck length is asking for the temperature of one molecule, not too small to measure, not a thing. There is a number that makes this reading concrete, and it comes out of black hole thermodynamics. The holographic bound says the information content of a region of space is limited not by its volume, but by its surface area, measured in Planck areas, roughly 1 bit for every 4 Planck length squares of boundary. Count the degrees of freedom available inside a Planck-sized region on that accounting, and you get about one bit. There is nothing left to count. Below that, geometry does not run out of resolution, it runs out of things to be made of. It is worth noting that the second response, the resistant one, has history on its side too, and it is not a foolish position. In the late 1800s, a great many serious physicists refused to accept atoms, on the grounds that nobody had ever observed one, and that a scientific theory should not traffic in invisible entities. Ernst Mach held that view essentially to the end of his life. The atoms were there. The strict rule, applied confidently in 1890, would have thrown away the correct answer. The reply to that is a fine one, and it goes like this. Atoms were unobservable in practice, not in principle. Nothing in the physics of 1890 said an atom could never be seen. It said the microscopes were not good enough yet, and eventually they were. What is different about the Planck length is that the impossibility is derived from the theory rather than assumed from present limitations. The equations themselves are telling us where they stop applying, which is a very unusual and rather generous thing for a theory to do. There is one more historical pattern worth holding, because it suggests what to look for next. Every time physics has retired an unmeasurable quantity, something came in to replace it. And what came in was almost always a symmetry. Throwing out absolute velocity gave us Lorentz invariance. Throwing out absolute simultaneity gave us the space-time interval, a quantity everyone agrees on, precisely because the ones they disagreed about were removed. If the continuum goes, something should arrive in its place, and it will probably be a principle nobody has written down yet. Nima Arkani Hamed has put the whole matter about as directly as it can be put. His observation is that every time physics has encountered ideas that cannot even in principle be observed, we have come to see those ideas as approximate notions. And what makes this instance particularly disturbing, in his words, is that the notion emerging as approximate is that of space-time itself. Early tonight I gave you a phrase, and I said it would change meaning 3 times. When you cannot make something out, bring a brighter lamp. The first time, it was simply true. The whole history of seeing, from a candle behind ground glass to a 27-kilometer superconducting ring, is that instinct being followed and rewarded. The second time, standing beside a machine 5,000 light-years around, it turned into a category error. The brightest lamp the laws permit does not light the room. It opens a hole in it. Here is the third. The lamp was never the problem, and neither was the room. The problem is that the room, the space, the distances, the between, is a description that works exquisitely well at every scale we can reach, and stops being a description of anything at all somewhere underneath us. We were not failing to see the flaw. We were finding out that the flaw is a word. That is why physics breaks apart beyond the Planck length. Not because the laws fail there, because the stage does. And we do not know what the stage is made of. That is the thread I am going to leave hanging, gently, because it is where the field actually is tonight. Strings, spin networks, causal sets, holographic boundaries, positive geometries with no space-time in them at all. These are candidates. Every one of them speculative, none of them tested. Somewhere beneath the smooth continuum, there is a structure that produces distance, the way molecules produce temperature, and nobody knows what it is. It is possible that no one ever will, in the direct sense, but it is also true that we found out this much from a question about microscopes, and that the whole of this evening's argument was available, in principle, to anyone who knew 3 constants and was willing to follow them somewhere uncomfortable. There is a strange comfort in that, I think. The universe turned out to have a flaw, and we did not find it by digging. We found it by sitting still and following 3 constants somewhere uncomfortable. Thank you for spending these hours with me, at the bottom of the smallest question there is. If this kind of slow exploration is worth something to you, a like or a subscribe genuinely helps me keep making them. And remember, The next time you look across the room and think you know how far away the wall is, underneath that distance, the question stops having an answer. Good night, and may you never quite trust the space between things again.